Okay, it's time to start. So it's my great pleasure to introduce Professor Chetan Nayak, today's colloquium speaker, HTP colloquium speaker. So although I think everybody knows about Chetan Nayak, but let me introduce about him briefly. So he was born in New York in 1971, and he graduated Harvard in 1992. And he got PhD in Princeton 1996. Maybe Frank Wilczek is your advisor? Yes, right. And spending several positions, one postdoctoral position and UCSB, and he became a professor in UCLA. Then interestingly, he became a senior researcher from 2005. Then he became full professor from 2007 at UC Santa Barbara. And now he is in technical fellow in Microsoft and also general manager of Microsoft. Yeah. And so yeah. So as you know, he's an expert in quantum topological field theory and topological quantum computation and condensed matter, theoretical condensed matter physics. So before starting, let me just briefly, I want to really, I have to share this slide just for, oh, sorry. I want to share this slide. Where is it? Huh? Okay. So, just a moment. Chetan Nayak. To show, his research interest and his record. So let me just briefly read. I think everybody knows his review article on non-abelian anyons and topological quantum computation. And also, previously in 2001, he wrote about hidden order in the QPrite and also minor fermion and topological quantum computation. And recently he did on flock at time crystals. So yeah, this is what he did. So I will not read the citation, but anyway, you can understand. So it is our great test. So feel free to ask any questions. So time limit is not restricted. Basically, Professor Chetan Nayak, you have 1 hour and 30 minutes, but everything is up to you. Yeah, so yeah, feel free to ask any questions, discussions. Yeah, please. Yeah.
Great. Thank you very much. And if someone raises a hand and I don't see it, please interrupt me and let me know that there's a hand raised. Okay. Thank you very much. Or I need to share a screen now, I think. So thank you for the kind invitation. It's a great pleasure to be telling you about this work, which I'm very excited about, and have a chance to explain it to you. This is work done with the team at Microsoft, so it's a large team, and I'm representing the contributions of many individuals. It's truly a team effort. So the motivation for this work is to try to make topologically protected, or it's on the journey to making topologically protected qubits. So topologically protected qubits take advantage of the fact that you can have situations which topology encodes in which there are very rigid, robust differences that are difficult to locally detect. So a topological qubit basically encodes quantum information in a non-local way, similar to how a Möbius band, which you have a picture here, encodes in a non-local way the difference between a Möbius band and an untwisted band. Locally, you can't tell the difference, but there's some important global difference here. And the only way you can change a Möbius band into an untwisted band is actually to tear it, take out the twist, and reglue it. which is kind of a violent operation. In the physical analog, there's an energy scale, delta, which tells you how hard it is. You can imagine a Möbius band made with very thin tissue paper, it'd be easy to tear, or something made of very thick, strong cloth, for instance, and it would be very difficult. You'd need scissors, hard to tear. So that's what the energy gap is measuring, is how hard it is to change the topology. In a topological phase, which topological qubits build on, the decoherence times are long, the gate fidelities are very high, and those are controlled by exponentials in that quantity, the energy gap. Also, the gate times can be short. Operations can be done relatively fast when that energy scale is large. And the footprint can actually be small too, because the size of a topological qubit is controlled by the correlation length. The correlation length is inversely proportional to the size of that gap. So you can have a short correlation length if the energy gap is large. Okay. So in fact, a topological qubit with a large energy gap solves many problems at once, which is having high gate fidelities, short gate times because you need to be able to operate it quickly, and also small footprint because you want your qubits to be relatively compact. The difficulty, of course, is up front. You must be able to reproducibly create a topological phase in devices. Okay, so that puts a challenge right up front. Being more specific about what those challenges entail, the first problem is, and the two key problems I would say are, disorder destroys topological phases. So they drive a phase transition into a trivial phase. The location of that transition as a function of controllable parameters depends on the material combination and device design. So what we have here is a TEM image of a type of device that I'll explain in more detail shortly, that involves superconducting and semiconducting layers. And you can see here, because this is grown by molecular beam epitaxy, the atoms are more or less perfect crystals in perfect atomic registry between one layer and another. Any disorder on top of that is extremely harmful because it will ultimately drive a phase transition to the trivial phase. So whatever, and of course it depends on the particular material combination device design, but however you manage to fabricate this thing, your process must be capable of getting you to the topological side of this transition. Otherwise you end up on the trivial side. That's problem number one. Second problem is that topological phases are difficult to detect. Topological invariants are not, in general, directly detected by bulk response functions. The quantum Hall effect is an exception. So those are the easiest things to measure. And so therefore, you need some model that connects the topological properties to measurable quantities. Okay. However, simulated data can test that connection. So there's some model-dependent and device-dependent translation from what you measure to topological invariants, and we can test those through simulations if we have a good model of the device. Okay, so those are the two key challenges, and those are the things that we've solved in this work, and that's what I'm going to tell you about. Okay, the particular topological phase, which is our focus here, is Majorana zero modes in proximatized semiconductor nanowires. So these are built on a semiconductor nanowire. And this is very schematic here. I'll explain how we make this and what it really looks like. Just schematically for now, we have a semiconductor nanowire, a barrier, usually just a larger band gap semiconductor, and then a superconductor. Okay. And an effective Hamiltonian for a very simplified model like this, for if it's single subband semiconductor nanowire, is what we have right here in the bottom left. Okay. And the various terms in this effective Hamiltonian can be understood pictorially in the top right. So there's the kinetic energy, which is just the dispersion at the bottom of the conduction band in the semiconductor, which you see right here. Then there's a spin-orbit coupling, okay? And we need large spin-orbit coupling. When the spin-orbit coupling is large, the bottom of the conduction can get split into two helicities, which look like this. And when we say large, we mean spin-orbit coupling larger than 4 MeV nanometers. Okay. We also need a large G factor. Okay. So G factor of like 10 to 50. Okay. And when we have what that means is when we put in a magnetic field along the wire, it will open up a gap at zero momentum that splits those crossed dispersions, opens up a gap there. And as a result, if you can control the density, you can arrange for the chemical potential to be in a place, or the density to be such that the chemical potential only intersects the dispersion intersects the band in exactly 2 points. So there's exactly 2 Fermi points, not 4 or a higher number. And when you only have 2 Fermi points, and you have a good interface with superconductivity, that superconductivity will necessarily be topological. Okay. So the name of the game here is construct some band structure with only 2 Fermi points, induce superconductivity, and you got something topological. This is a highly simplified model. Okay, very idealized. However, what we're going to do now is I'm going to explain how we can design a device that actually makes this, that sort of makes reality look like the simplified model. Okay. Within that simplified model, there are 2 phases. Why is this model so interesting? I said it has a topological phase. There's 2 phases. I'm going to generally use red for the topological phase and blue for the trivial phase. Topological phase occurs at high field for some range of densities, which translates to chemical potentials. The blue phase occurs at low fields. In the trivial phase, the blue or trivial phase, it's classic BCS density of states, no states underneath the gap. And then in the high field phase, it's actually almost the same density of states. This is the local density of states, so this is energy here versus position along the wire here. And there's a gap in the bulk of the wire, but at the ends you have these Majorana zero modes. These which are and the symptoms, the signatures in the density of states are these peaks in the local density of states at the ends of the wire. Okay. Now, again, that's very highly simplified and idealized model. How can we get something in reality that looks like that? Well, our approach is with gate-defined nanowires. These are built on indium arsenide 2-DAG. So this is a side view, cross-sectional view of our material stack. There's a substrate, a buffer, an indium arsenide quantum well, and a barrier layer. Okay. On top of that barrier, there's a superconductor, aluminum. So it's a very thin aluminum strip like this into the plane of the slide. That aluminum strip induces superconductivity in the indium arsenide quantum well. And there's also a dielectric and gates. The purpose of gates will be clear shortly when we take a look at a top view, okay? And we see the top view, the gates in top are actually separated or divided into 3 sections, okay? A middle, a right, and a left. And what these gates do is when they're energized, meaning whether we put negative voltage on them, they deplete the 2-dimensional electron gas, they deplete the indium arsenide quantum well almost everywhere. Everywhere that's not covered by aluminum is fully depleted. And out on the sides, where it is covered by aluminum, it's also depleted. But underneath the middle section covered by aluminum, it's not fully depleted because the aluminum partially screens the electric fields from the gates and leaves some density down there. Okay. And then there's also some sort of helper gates over here that are actually at positive voltages that bring some density in from the sides so that we can perform tunneling measurements in which we tunnel some current into the device. Out here, the gates are more negative, so they deplete even underneath the superconductor. And here the gates, we exercise some freedom to control the density so that it's low and in the lowest subband, but not, or I should say, we'll see momentarily that it needs to be in the lowest subband, but we can tune the density here with this gate and it doesn't necessarily have to be fully depleted. Okay, so this is how we have a gate-defined nanowire underneath a superconductor. Okay, if we put a magnetic field, we tune that density just right, put a magnetic field along the wire, then we will enter the topological phase, and there'll be a local density of states that looks like this, and those are the signatures of Majorana zero modes at the end of the wire. Okay.
I'm sorry.
Are there any questions so far?
Yeah, elementary question. So I missed two. So superconductivity is assigned to aluminum. So applying gate voltage, you mentioned about screening. What's the effect of gate voltage to aluminum?
Nothing. There's minimal effect of the gate voltage in aluminum because aluminum is a metal and it's grounded and has very high density. So the aluminum is grounded at the sides. It doesn't really care. Its density is too high. You can't change the density inside of aluminum. You know, a big long aluminum wire. The semiconductor has much lower density, 3 orders of magnitude lower. And so with the gates, we can change the density in the semiconductor.
I see. Thank you.
So. Okay, so that was schematic. Here's what an SEM image of an actual device looks like. Okay. Now, with a concrete device in hand, we can revisit the question of the phase diagram. As I said earlier, disorder is extremely important, but for a moment, let's even just consider the completely clean case with no disorder, which already has some interesting features, and then we'll reintroduce disorder. Yeah, you recall the highly simplified model had a phase diagram that looks like this, with topological and trivial regions. The phase diagram of the device I just showed you in the absence of disorder looks like this. So the color scale is still blue means trivial and red means topological, but now I've introduced shadings of blue and red, so darker blue and darker red, paler blue and paler red. And that you can see over here, the color scale what the color scale represents is just how large the gap is in either the trivial or topological phase. So darker blues are in the trivial phase with larger gap, and darker reds are in the topological phase with larger gap. Now, what you can see is the phase diagram is more complex. Whereas there was just one topological region here, there are several topological regions. Those correspond to, as I said, the simplified model is a single subband. This corresponds to one subband, three subbands, five subbands. So with any odd number of subbands, because the wire is not truly one-dimensional, it's quasi-one-dimensional. It has a finite extent in the y direction. You'll also note, so this, another important point here is that these are the actual control parameters of the device, whereas over here, this was a effective parameter, which is the chemical potential, and the Zeeman energy. Here, we're talking about the actual plunger gate voltage, which, how it affects the chemical potential is dependent on the lever arm, so it's dependent on screening and the geometry of the device. Over here, there's the magnetic field, and how much Zeeman energy depends on the G factor, which is normalized by the coupling between the semiconductor and the superconductor. So these are actual control parameters that you could compare directly to the parameters you control on an experiment. Secondly, the wire is not truly one-dimensional, it's quasi-one-dimensional. So actually the magnetic field has, in addition to the Zeeman energy, it has orbital effects, and the orbital effects suppress the superconductivity, both in the trivial and in the topological phase. They simply suppress how much superconductivity you can induce in the semiconductor. And so you can see here that what's actually happening here is this is when the magnetic field is large enough to thread half of a flux quantum through the full cross-sectional area of the superconductor-semiconductor sandwich. Okay, so that's extremely bad for superconductivity, and that's why you can see what you see here. An important feature of this phase diagram is that actually the lowest subband, meaning when only a single subband is occupied, is highly advantageous for the topological phase. Okay.
One simple question. Is it possible to have FFLO because you apply the X direction for magnetic field? Yeah,
this is this system has strong spin overcoupling. So as a result of the strong spin orbit coupling, instead of the FFLO state, you end up with the magnetic field is not large enough to induce FFLO state in the aluminum, and it doesn't induce it in the semiconductor because of the large spin orbit coupling.
I see.
Yeah.
Okay, thank you.
Yeah, because in the semiconductor, we don't have two Fermi surfaces. The FFLO has like an upspin and a downspin Fermi surface. In the semiconductor here, we have only one Fermi surface because the spin is locked to the momentum.
But if you apply magnetic field, I see. Okay, I see. Yeah.
Yeah. FFLO requires two Fermi surfaces. One of them becomes large and one becomes smaller. And but we don't have two Fermi surfaces here. We have or two Fermi Cs. We have only one with spin locked to momentum. So you could have it in a different density range, but we're tuning into a density range where you have only an odd number of subbands. In fact, it's clearly advantageous for us to have only a single subband. Okay, so that's clean system. So already with clean system, we learned something important, that actually it's very advantageous to actually have very narrow wires, because the narrow wires will have a bigger spacing between subbands, and you can more easily tune into the single subband regime. Okay, which is a helpful place to be. Now we got to consider disorder. So there's various types of imperfections that are inevitably present. There's going to be, all kinds of disorder in our nanowire. As a result of that, Random potential, an electron going through the wire will bounce around all over the place. The disorder strongly suppresses the topological phase, and it can nucleate regions of topological and non-topological phase, creating low energy states. Okay, and so as a result of this, if we look at our phase diagram now in the presence of disorder, this is just a certain root mean squared variation in the potential in the wire. What you can see is that parabolic shape we saw in the perfectly clean system gets kind of broken up and breaks, and it's a parabolic shape, but there's regions here of trivial phase, and red here is everywhere that it's a topological phase. And in fact, if you require not only that it's a topological phase, but also topological phase and a gap larger than some minimum value, which is 10 microvolts, then you can see the topological phase breaks into even smaller regions. So disorder changes the look of the phase diagram significantly, breaks a large parabolic topological region into these small fragments. Okay, and ultimately, when the disorder gets too strong, you don't even have those, and the topological phase is completely gone. Okay, that occurs at a critical disorder strength, which is when delta, which is the ideal clean system gap times tau, is of order 1, or equivalently, when the localization length in the wire is equal to the ideal clean system coherence length. Okay, so disorder is the enemy in this sense, and even before disorder destroys the topological phase, it breaks this big topological parabola into these smaller fragments.
What is the black region?
This region here?
Black. Yeah.
Black is when it's topological and the gap exceeds the minimum value of 10 microvolts. So it's topological with a sufficiently large energy gap. And that's a pretty low, threshold, only 10 microvolts. So it's really saying all this other red region is technically topological, but the gap is very small. It's less than 10 microvolts in this red region. The black region, these fragments, that's where you have, you could say, a topological phase with at least, a non-negligible energy gap.
So in this case, so if I recall the topological insulator with disorder, some parameter range, we can observe so-called topological Anderson insulating phase. So in this case, what happens? So is there analogous phase or for?
Yeah. So okay, this is a one-dimensional system, not a two-dimensional system. So because this is a 1D system, actually all states are ultimately localized. Okay, so other than potentially the phase transition zero energy states, all states are localized. So in that sense, it does have that property of an Anderson insulator. However, even though all states are localized, the system may be topological or non-topological. This is the situation. This is a finite length wire. Now, in a finite length wire, okay, in an infinite wire, there's no gap, because the gap will fill in with localized states. This is a wire of finite length, like 3 microns long, which is, as it turns out, is how long the wires in our system. So many of the states have at this disorder value have localization lengths that are longer than the wire length. And so effectively they're delocalized states at the system size. So in a wire of this length for this disorder level, there is actually an energy gap. Okay, it doesn't fill in with localized states. And this is an energy gap greater than 10 microvolts.
Then basically some fractal feature of wave functions and some topological nature appear at coexist. So in actual sample.
Yeah.
Okay, I see. Thank you.
They do. Correct. Okay, so we need to keep the disorder low in order to have these regions of topological phase at all, since the localization length needs to be comparable to the clean system coherence length, or preferably longer. Now, there are many types of disorder, potential disorder, and potentially there are many types of disorder in a system like this. There's dislocations like screw dislocations that might be coming from misfits in lattice constants between the different layers. There could be alloy disorder. There could be charge defects, both in the bulk and the interface. Okay. it turns out that at low density, which is we're in the low density limit because quasi 1D system, lowest subband, the dominant source of disorder is charge defects at the dielectric interface. Okay, so there's a dielectric here, okay, which insulates the system from these gates. That dielectric has defects that are charge defects right at the interface of the semiconductor. They're the dominant source of disorder in this system. Okay, and so what the design does, it keeps these defects as far from the active region as possible. So we want to maximize this distance. So that's helped by making the aluminum strip wider, as wide as possible. However, we can't make it too wide because then we will not be able to deplete into the lowest subband and the orbital effects will be large. And we know that we need to be able to deplete to the lowest subband, the orbital effects need to be small. So we make the aluminum wire as wide as possible, but not too wide. Second thing is, if we make the barrier layer here thicker, then we move the wave function further away from the charge defects, and that also helps. However, we can't make it too thick because if we make it too thick, then the induced superconductivity is too small. Okay, so there's a Goldilocks regime of a barrier layer that's thick enough but not too thick, and an aluminum strip that's wide enough but not too wide. Okay, so it's the width of the aluminum strip and the thickness of the barrier layer. Two things we can control in the design. Once we have optimized those, made the aluminum as wide as possible, but still depletable, and made the thick barrier layer thick enough, but still inducing a healthy induced gap, then in that circumstance, we need a density of charge defects that's less than around 3 times 10 to the 12th, okay, from our simulations. And so that's the target. And we've developed fabrication processes that indeed minimize the density of such defects. Okay. We confirm this by actually measuring directly the localization length underneath the aluminum. We modified our device design a little bit to add, so that we, instead of having 2 tunnel junctions, we have 4 of varying lengths, so that we can measure non-local conductances or transconductances between different pairs of leads, and thereby in the same wire measure the conductance across different lengths. That non-local conductance is the derivative of the current at the right junction with respect to the voltage of the left junction, normalized by the local conductances is supposed to decay exponentially with the length of the wire, which again we can vary by choosing different pairs of junctions. And what we see is that here's a map of the non-local conductance as a function of bias voltage for different plunger gate voltages, which is different densities in the wire for different lengths. So that's for different pairs. This is lead 1 to lead 2, 2 to 3, 1 to 3, and so on, all the way up to the 1 to 4 from here to here, which is the longest one. And across these different lengths, you can see how it decays exponentially, but there is signal even at 8 microns. And if we plot this on a versus plunger gate and localization length as a function of plunger gate, when we are at low plunger gates, somewhere around here, where we're in the lowest subband, okay, around here, the localization length is larger than a micron. Okay, it's a few microns. And we expect from simulations that the size of the ideal clean system coherence length will be less than a micron. So we're in the happy regime where the localization length is longer. Okay, we expect the clean system coherence length actually be about, like, a third as large. So this is in a good limit in which the localization length is, you can see, is relatively large. Okay, so now we know we have a specific device design. We know what its phase diagram looks like. We know how clean it has to be. Okay, and we verified that it's clean enough. Okay, now of course we have to face it with problem number 2, which is we've got to actually find the topological phase experimentally. So we introduced this topological gap protocol to do just that. And what the protocol does is it comes in 2 stages, and it does 2 things. First, it looks at the local conductances, and it looks for a zero bias peak in the local conductance. So we take the derivative of I right with respect to V right. That is dominated, and the derivative of I left with respect to V left. Those are dominated by a current that flows into the device here and then goes off this way, or flows into the device here and then goes off this way, depending on whether it's GRR or GLL. What we're looking for are zero bias peaks. So when this conductance is peaked at zero bias, that means there's a zero energy state in the wire that that we detected through this conductance measurement. And we want them, and we want them to be stable at both ends of the wire. So we want to see them at both ends of the wire. We want them to be stable. We also want them to be stable over an extended region in phase space, so the bulk phase diagram. So they need to be stable with respect to opening or closing these junctions more, changing the junction transparencies, and also stable with respect to pushing up and down the plunger gate voltage to change the average density and also magnetic field. Okay, so we'll find regions in phase space this way that have stable zero bias peaks. In stage 2, we actually turn the problem around and say, it might be easier or instructive to look not where the system is in the topological phase, but where there's a phase transition from the trivial to the topological phase. So we look for a gap closing and reopening in the non-local conductance. And that's a sign of a phase transition out of the conventional or trivial superconducting phase. So we look at the non-local conductance. That's dominated by, looks like this. At low bias voltage, it's basically zero because you can't push any current in. The system is gapped. The semiconductor is gapped because it's inherited superconductivity. The superconductor is gapped. If we go to very high bias above the gap of aluminum, then you can just push the electrons straight into the aluminum. The aluminum is grounded, they just run to ground. And so they never come over here. But if the bias voltage is between the induced gap in the semiconductor and the parent gap of the superconductor, the charge that we push in stays in the semiconductor, can't go into the superconductor, and then it can only come out over here. So the derivative of I left with respect to V right is 0 at high bias, 0 at low bias, less than the induced gap, and non-zero between the induced gap and the parent gap. And so when the system approaches a phase transition, this region in which it's 0 shrinks as the induced gap goes down to 0, shrinks away, and then reopens. So we're looking for a gap closing and reopening the non-local conductance. That's a phase transition out of the conventional trivial superconducting phase. And then we put these things together. We check to see if there are regions with stable zero bias peaks that are gapped, but the boundary of those regions is gapless. And if that's the case, the device is past stage 2. The device demonstrates the topological phase, and we extract the topological gap. Okay.
Question.
Okay.
Simply, I think I didn't understand so how to observe the phase transition based on non-local conductance. Will you just repeat again? Sorry.
Yes. So we look for phase transition by looking for when the gap closes. We look at the bulk gap, see when the bulk gap closes. Okay. Because at a phase transition, at second order phase transition, the gap should close. So this should be gapless at the transition point.
Yes.
Okay. So we're looking for where the gap closes. The non-local conductance is the derivative, say, of I left with respect to V right. The non-local conductance vanishes at energies below the induced gap, below the gap of that's induced in the semiconductor. Because below that gap, you simply can't put any charge in because the system doesn't have any states there. So it's 0 here. And it's at bias voltages larger than the aluminum gap, it's 0 because you can put charge in, their states there. But if they go straight into the aluminum and the aluminum is grounded, so that charge goes to ground. There's no reason for it won't come over here. It'll go straight to ground, take the easiest path. The only place where there's a non-zero signal is between the induced gap and the parent gap, because above the induced gap, the charge can go into the semiconductor, but it's below the aluminum gap, so it can't go this way. Because remember, here and here, the semiconductor is fully depleted, so there's only aluminum out here. So it can't go to the left and to the right. The only place the charge can go is through the middle of the wire and come out over here. And that's why the non-local conductance, or GLR, and similarly GRL, is 0 beneath the induced gap. And as the induced gap goes to 0, which is as it approaches the phase transition, this region right here keeps shrinking down.
Clear, thank you.
Sure. And here is what that transport data looks like. And this is transport data on our device as we vary. So this is here, the magnetic field is varying. So this is sort of bias voltage in this direction, magnetic field in this direction. This is G left, left, G right, right, G left, right, G right, left. Okay. Or other way, G right, left, G left, right here. And you can see there's a movie, and what's changing in the movie is we're changing the plunger gate voltage, so we're going to different densities, and we're also changing the junction transparency, so we're opening or closing the junctions more. So we're both changing the local potential and we're changing the global potential. And you can see there's regions where you have stable zero bias peaks. There are regions where you were asking about the gap closing. Anytime the non-local conductance comes down and the blue and red regions touch each other close to zero, that's where the gap is closed for that value of magnetic field and that value of the plunger gate voltage. The topological gap protocol takes this entire kind of movie, which is this transport data for all four entries of the conductance matrix over a range of plunger gate voltages, magnetic fields, and junction transparencies. It analyzes that and turns it into, among other things, a phase diagram. And in this phase diagram, which we can represent in two ways, here's one way. These are the gap regions that do not have stable zero bias peaks. There are white regions, which are gapless and do not have stable zero bias peaks. There are the yellow regions that are gapless and do have stable zero bias peaks. And then there are the orange regions, which are gapped and have stable zero bias peaks. And if those orange regions also have gapless boundaries, then they are strong candidates to be in the topological phase. This hatched region here, since it's a simulation, we actually know where the scattering of the topological invariant is equal to -1. And so this whole region here has topological invariant equals -1. Okay. And so what we're doing here is we're comparing the result of calculating the topological invariant, which we can only do in a simulation, to the output of a transport measurement, which we can do both in simulation and experiment. And what we see is, with this simulated data, the topological gap protocol finds a topological phase over here. There's lots of sort of small gap or gapless regions out here. The trivial regions are out here where it's a gap trivial superconductor. And what you can see is what the TGP identified. This color scale shows how large the gap is, and what the TGP, what you can see is this identified topological region actually does have scattering invariant equal -1. Okay, so it's in fact in the topological phase by that measure.
Oh, question.
We did this. Yeah, sorry, go ahead.
So zero bias peak can be still protected around the gapless environment?
Well, yeah, so the zero bias peak, there's no gap, so it's there's no reason for it to be protected, but there can be accidentally, there can be zero bias peaks, and sometimes they're stable. I mean, that's what this yellow region over here is showing. What is probably happening is in those regions, the gap may not be quite zero, it may just be small, and we can't resolve small from zero. The second thing is those disorder regions might have, what they often have is, you can see sometimes in these figures, you see the zero bias peak comes in earlier before the gap is reopened, before you go into the topological phase. And sometimes these are called like quasi-Majorana zero modes, because it's like a precursor. What's happened is the ends of the wire have gone into the topological phase earlier and have stable zero bias peaks before the full bulk phase transition occurs.
I'm sorry, so before topological phase transition occurs, zero bias, quasi whatever, seems to appear.
This is simulated data, and in the simulations that happens. Yeah, this is all simulated data, and in the simulations, this is quite common to have stable zero bias peaks appear before the actual topological phase.
So how can I understand that?
That is two things to point out. First of all, here, technically, this whole region here is topological. See, it's all hatched. So this yellow region, there's a very small yellow region here that's not hatched. Most of this yellow region is hatched. So it is topological, but the gap is very small. The gap is smaller than our threshold, because here we're setting a threshold of about 10 microvolts, and it is topological, the gap, but just very small gap. Okay. Then on top of that, there are some regions like this yellow region here, where there are stable zero bias peaks, but it's not topological, or not yet. And that's just because it's an inhomogeneous system, and near the junctions, the potential can be different than in the middle of the wire. And sometimes in the junctions, you go into the topological phase first, and then later you go into the topological phase in the bulk of the wire.
I see. Thank you.
Yeah. So we did this we simulated the device, many realizations of disorder. Okay. and we compare the output of the TGP, the topological gap protocol, to a topological invariant. Okay, because the topological gap protocol just takes some transport data just like you would in an experiment. It doesn't directly access the topological invariant, and we want to compare those two ways of analyzing it. If they agree, then it's a true positive, but if the TGP found a topological phase that's not there, then it's a false positive, and that means the device only has a trivial phase but passes the TGP. And then the false discovery rate is a probability that when the TGP finds a topological phase, there is none. Okay, and here's the statistics from our simulations. What you can see is actually we found no false positives. The false discovery rate is we've quoted is what you would get for from the binomial distribution given these sample sizes. And so this is only limited by number of statistics, but you can see the false discovery rate is low. Okay, it's less than around 8% at the 95% confidence level, and that's for one particular. These are slightly different device designs and different disorder levels, different densities of charge defects. For the vast majority of these, the false discovery rate is actually less than, less is a 5% or less. Okay. So this tells us we can have significant confidence if something passes an experiment, the topological gap protocol, then in fact there's topological phase there.
One more question. So in the previous page, so because as you mentioned, it's quite inhomogeneous. So actual topological region and non-topological region are quite mixed, and so indeed, so the zero bias peak, a region where zero bias peak exists, maybe identify some locally some topological phase is realized, or so separated.
Sorry, I don't think I really understand. Can you say what the question was?
So my question is, so the coexistence between gapless phase and zero bias peak, and also some precursor of the appearance of precursor of zero bias peak, maybe due to some separated realization of topological region and non-topological region in this.
Yes, it could be different parts of the device. That is one possible mechanism.
Okay, thank you.
Yeah, agreed. Okay, so now experimental data from real devices. So here's an SEM image of one of our devices. Topological, the actual energy gap is measured in this region here. Here's where the Majorana zero modes would be in the topological phase. This is a device we call device A. We actually measured this device multiple times in multiple cool downs, actually in different locations with different people. And here's the phase diagram we get. Just like the phase diagram we get with simulated data, here's the phase diagram we get from real experimental data. Here is a region where the system is gapped. There's zero bias peaks. The boundary is gapless or predominantly gapless. Out here is kind of the trivial phase, and the white and yellow is where you're in the critical region, okay, in this disordered system. If I look here on this color scale showing the size of the gap, you can see here's the region that we identify as topological. It's a gap region surrounded by gapless areas in the phase diagram, and there's stable zero bias peaks here, okay? So this is what you really expect topological phase to look like in a system like this, okay? The maximum topological gap in this measurement, this device, is about 23 microvolts. And so the area of the topological phase is a multiple of that topological gap squared. So it looks like potentially a small region here, but it's actually the right size given how large the gap is. Okay, and that phase diagram it comes out of analyzing an automated analysis, I should say, of data looks like this. So here's what the transport data looks like. Here's the gap closing and reopening, and the non-local conductance. Here are the zero bias peaks, which this is for one particular value of junction transparency, but they're stable in this device at that point over multiple junction transparencies. Here's another way of representing the same data, of representing the four conductances as a function of magnetic field and bias voltage. You can see zero bias peaks appearing here and here that are stable, and the gap closing and reopening like this. This is one slice through the data for one Cutter gate setting, but actually every pixel here is derived from both the local and non-local conductances as a function of junction transparencies, bias voltage, magnetic field, and plunger gate voltage. Okay. We actually measure the same device again. So here's a second measurement in a second cool down. Turns out in this measurement, every time we do a cool down, the disorder of the charge impurities move around a little bit, so the phase diagram doesn't look exactly the same, but it looks similar. The gap size is similar. In this case, it's about 29 microvolts. The area of the topological phase is again a few times the topological gap squared. So, and then we actually saw similar data in a number of devices. We took that understanding, made some improvements to get larger topological gaps. We further optimized the material stack and device design. We were able to reduce the disorder level a little bit. Here is one of these sort of second wave devices. One of the changes you can see is that whereas before we had split gates over the aluminum, here it's a single plunger gate, okay? And then with the single plunger gate here, we need some additional extra second layer gates over the junctions in order to enable junction operations that you could fully open and fully close it, even while the single plunger gate was being pushed fairly negative. And we actually saw in this new design a device with quite large gaps. So here's a device with a 60 microvolt topological gap, and here's a topological region in this phase diagram. We also saw devices that didn't have a topological phase that, and we still do. There's some fraction of our devices that only have trivial phase. They fail topological gap protocol. Here's an example of such a device. It had stable zero bias peaks at both ends, like these yellow regions, which are actually reasonably large. And then if you look at the phase diagram here in this blue-red color scheme, you can see it's all pretty trivial. There's just all sort of pale blue. There's no place where the gap reopens with stable zero bias peak. So this is an example of what a quote-unquote boring phase diagram in a failed device looks like. In this case, the particular device, there's some natural variation in what the density of charge defects is in our devices. This one happened to have a little bit higher defect density, but even the ones with lower density, the yield isn't perfect. It's a mesoscopic system, it's a finite size device, and the disorder levels are small, but not extremely small. Okay, here's what the transport data looks like, cut through here. You can see there are stable zero bias peaks on both sides, but the gap really never reopens. It gets small and then kind of stays small.
Maybe you already mentioned, how can you control the disorder around the aluminum was the
process. Yes. So the key disorder level is the key disorder is charge defects at the interface between the semiconductor and the dielectric, and so the disorder is controlled through surface treatments of the surface before the dielectric is deposited, and the precise dielectric deposition recipe, which includes temperature of deposition, length of annealing, temperature of annealing. So various ways to try to make the dielectric as high quality as possible.
Thank you.
Okay. So that's inducing Majorana zero modes in a single wire. Now we're going beyond that. So we want to make qubits. We need to control the Majorana zero modes. So here is, again, this is just to repeat, this is what our topological gap device looks like. This is a gap where we can induce the topological phase, measure the gap. Now we need to go beyond that, okay? And so this thing schematically has Majorana zero modes at both ends of the wire, topological region in the middle, trivial regions on the side, because we fully deplete on the sides. The next level of complexity is two topological regions. So there's a topological region here, topological region here, Majorana zero modes over here. So this has now 4 Majorana zero modes. Now we can make a qubit with fixed total parity, in which these two are even. The fermion parity here is even, and here is even. So even, or odd, which is still all overall even. Then we have, in addition, we have quantum dots over here. Okay, So these quantum dots are tunnel coupled to the Majorana zero modes. So you can tunnel to the Majorana zero modes. That tunneling actually shifts the energy level spectrum in the quantum dot. And by shifting the energy level spectrum, it changes the average charge in the dot, and it actually changes the capacitance as well, which is the second derivative of the energy with respect to voltage. That capacitance shift depends on the parity shared by the Majorana zero modes. It's effectively an interference process along a loop like this. And so by seeing for one parity, the capacitance looks like this as a function of gate voltage, and the other parity it looks like this. So the shift in capacitance caused by the coupling of Majorana zero modes can be quite different for the two cases, for the two total parities. So that's what ultimately you would measure in order to measure the fermion parity shift, or equally well to measure this qubit in the Z state, do a Z measurement. Similarly, you can measure this quantum dot to do an X measurement. And this quantum dot, if the total parity is fixed, would be another Z measurement. Either one of these would give you a Z measurement if you measure the shift of the capacitance of that quantum dot. And continue to look ahead. So this is the simplest qubit, topological qubit you can make with two topological segments, and you can measure topological fusion. You can measure fusion of anyons here, the fact that there are two outcomes for the fusion of two anyons. To see braiding, you need an even more complicated device. So here, it's actually helpful to go to, whereas here, our 4 Majorana zero modes were on two wires that were collinear. It's advantageous to go away from the collinear geometry towards an H-like geometry with trivial superconductor here. And in that H-like geometry, you have 4 Majorana zero modes on a qubit. Here's a second qubit with 4 Majorana zero modes. And here's a coherent link between the left and right sides. And now there's various quantum dots over here that we can measure. And in a device like this, you can actually demonstrate braiding. Okay. So with that, I'd like to thank you for your attention, and I'm happy to take questions.
Thank you very much for very interesting talk. So now the talk is open for questions. So really, so turn on your, yeah. So there is one question. Can you give us your comment on the value of zero bias conductance peak, which seems to be below E square over H?
Oh, the value. Well, the value of the zero bias conductance is an excellent question. It depends on how open or closed the junction is. Okay, so if the junction is very open, it will be large. And if the junction is very closed, it will be large, and it will go towards 2e squared over h. If the junction is closed, it can be very small. What we did is we stayed for relatively closed junctions. So our above gap conductance is less than e squared over h. So we keep relatively low conductance values so that there's a simple tunneling interpretation of what we're measuring, that we're measuring, local density of states. We measure, the junction settings are the same for the local and non-local conductances, and we want the non-local conductances to actually be measuring the size of the bulk gap. So we can, it is not, the value of the zero bias peak is not a bulk topological invariant. You could get 2e squared over h, and it could be quantized even if you're not in the topological phase. So we, did not have any reason to try to tune the junction so that it would give us a quantized value. What we found is through our simulations that the value didn't matter much, but as long as we had zero bias peaks that were stable, the stability was more important, that they were stable, that we could measure a gap in the bulk, and that there was a phase transition going through a gapless region from the low field side, then our simulations show that statistically it's extremely likely that you're in the topological phase.
Yeah, he said, yeah, thank you. So more questions? Yeah, please. Yeah, stop from John.
Okay, yeah. Thank you very much for your talk, Chetan. So just before I head off to my class, my question is, so when you're talking about how to realize braiding, you showed us the figure with what looked like five qubits. So I'm just wondering whether you mean this to be a kind of like a minimal requirement for realizing braiding, or
it's actually 2 qubits. It's 2 qubits. This is 1 qubit here. This is 1 qubit here. This is actually a coherent link from the left to right side.
Oh,
because
so you-
yeah.
I mean, the Majorana zero, it seems like you have pair of Majorana zero mode in the middle along this.
Yeah, that's
at
right.
the
So
end of
this
the
is
purple
actually,
region.
this is not a qubit though, because each of these, this is floating. So this has total fixed charge and four Majorana zero modes. So that's one qubit. This is also floating, okay, because there's gates here that pinch it off. This is also floating, it's not grounded, and it has 1, 2, 3, 4 Majorana zero modes. It's also a qubit. This is floating, it has 2 Majorana zero modes, it's not a qubit at all, but we can use it as a coherent link, because what we can do is, if we want to measure, let's say Z is the parity shared between these two, then we measure capacitance on this quantum dot. However, if we want to measure the parity shared between these two, then actually we use this link to make an interference loop like this. So we're really just using this as a way to have a long coherent link. It's floating and doesn't have any degeneracy, but you can insert it into a loop like this, and now as a result of this link, you actually can measure the parity shared between here and here.
Yeah, so I mean, is for realizing that, I mean, is having the pair of Majorana zero mode at the middle, I mean, is that a necessary requirement, or
Yeah,
I mean,
you
it's possible
need
to have some alternative?
This is a measurement only scheme, so measurement only quantum computation. So with a measurement only scheme, you need a minimum of 6 Majorana zero modes to do braiding. So there is a different device design in which you could have a qubit with 6 Majorana zero modes, then you could do braiding within that single qubit. But that is actually less convenient for layout and for scaling. So in terms of what what a scalable system will look like, is it has qubits with 4 Majorana zero modes.
Oh, okay.
We
Thank
could
you
in
very
principle do it with just 6. This one has, you can see this one has more, this one has 10. So it's not minimal in that sense, but it's minimal scalable.
much. Okay. Thank you very much.
More questions? Let me just, I'm somewhat curious in the last slide. So will you elaborate how to detect some fusion? I mean, you mentioned some checking out parity in the previous pages. So, yeah. So
These 2 Majorana zero modes, their fusion is either, they fuse either 0 or 1, or sometimes it's called 1 or psi. And so those fusion channels correspond to even odd fermion parity. The capacitance, when tunneling is turned on, the capacitance of this dot is shifted in such a way that it's sensitive to the parity. So the capacitance shift is 1 value if the parity is -1. It's a different value if the parity is +1. So if we embed this dot, if you put it at the end of a transmission line with an inductor in series with it, then we have an LC circuit. A capacitance shift turns into a shift of the resonance frequency of that circuit, which we can dispersively measure. And so by measuring the response of that resonator, we can measure what the capacitance shift was, and through the capacitance shift, we can measure the parity of the Majorana zero modes. And we can, in fact, we'd be able to see 2 different values, that you get either 0 or 1. You could get 2 different values for the capacitance shift, either this or this.
what is the braiding measurement protocol? In the last page, next page. So
yeah. So in a measurement only protocol, you can do a sequence of measurements in order to implement a braid. So you would measure the parity of these 2 first, then you'd measure the parity of these 2, this one and this one, and then you would measure the parity of this and this. And by doing 3 parity measurements, you end up doing a braid.
I see. Okay, thank you. Any more questions? If not, I think it's time to close. So let's thank speaker again, Professor Chetan Nayak. Thank you very much.
Thank you.
Thank you very much. Yeah. So the officially end. Yeah.
Okay.
Okay. Yeah. Yeah.
Thank you very much.
Yeah.
I
Yeah.
appreciate it. Thank you.
Yeah.
Bye-bye.
Thank you. Yeah. Bye.